Okay, I think we should start. There's like enough people to start. So let me introduce myself quickly. My name is Boris. I'm the cloud architect with the Nebius AI. Today, we're going to talk a little bit about RAG architecture. We have some experience with our clients when it comes to inference on Kubernetes. So we would like to share that with you. Let me share my screen. I will be talking a little bit about RAG architecture, techniques and technologies used, but mostly focusing on production considerations, challenges you will be facing with production. We had experience with our clients regarding inference, as I said, on Kubernetes, and we're constantly optimizing and improving our solutions. So something we'd like to share with you. And there will be some demos as well. So RAG, retrieval augmented generation. It combines the information retrieval with the text generation to produce more accurate and contextually relevant responses. And it also reduces hallucinations that a model might have. Retrieval involves searching large documents or databases. It can be either or some knowledge bases like texts and documents and whatever. To find relevant information based on a given query. It uses several retrieval algorithms and to rank and fetch the most relevant documents of data. Specifically in this presentation, I will be focusing on the RAG example that NVIDIA created. So this is like what it looks like, simple diagram, what this particular example looks like. Typically in RAG, we have like a query input, user provides a query prompt. Then there's a retrieval step in which this chain server is going to search a database to retrieve relevant documents. In my case, I will be using vector database, specifically Milvus database. And then augmentation step is going to be like the retrieved information is combined with the original query to form an augmented input. And then we get to the generation step, which is where we are going to use a combination of Triton Server with TensorRT engine. The augmented input is fed into the language model, which generates the final response. And then we get this response to a user, basically. So as I said, this example is like TensorRT with Triton Inference Server. TensorRT is NVIDIA's SDK for high performance deep learning inference on NVIDIA GPUs. It optimizes learning models for production environments by reducing latency and increasing throughputs. It improves performance through optimization techniques like layer intention fusion, precision calibration. It supports floating points 32, 16, and int8. And it supports wide range of applications and networks, facilitating easy deployments across various devices for like without sacrificing speed or accuracy. Then on top of it, there's a Triton Inference Server, also NVIDIA's open source project. It standardizes AI model deployment and execution across every workload, offers a unified architecture to serve models from multiple frameworks. So there's a lot of backends like for TensorFlow, PyTorch, TensorRT, and loads more. Also, there's like a concurrent architecture, which allows multiple models or even multiple instances of the same model to be executed in parallel at the same time. And the system may have a 0, 1, or multiple GPUs. It supports in-flight batching. It enhances throughput by dynamically batching incoming inference requests, effectively managing varying load scenarios. And then for the vector database, in this example, we will be using Milvus. Milvus is designed specifically for handling vector Vector similarity searches at scale, crucial for applications like image retrieval, face recognition, recommendation systems, so on. It supports multiple index types, and it's highly scalable. It builds to scale horizontally inside the cloud. It creates like a big cluster. It facilitates billion-scale vector databases and real-time searches in distributed environments. It also offers GPU acceleration. So GPU acceleration can improve the search performance and efficiency of Milvus, especially in like a high throughput scenarios, high throughput, low latency scenarios. And let me just stop this and show you what it looks like. So if I end here, so this is the example that we will be looking at. This is NVIDIA's generative AI examples. You can find it on their GitHub. And basically, let me show you what I've done in our console. So this is Nebius AI console. This is my sandbox environment and my folder. In here, I have, I'm currently hosting a couple of things, but most notably here I have this dev machine, which is running 2 GPUs. And yeah, in our console, there's a cloud marketplace where you can create different types of different flavors of compute instances, as you can see here. So some of these are like, well, most of them are AI ML specifics. So for instance, like this data science virtual machine and all of the others as well. Basically, the idea is that you already have pre-installed Cuda drivers, all the necessary things, frameworks and such, so that you can start working straight away. So that's what I've done. I've already prepared a dev machine from this image, and this dev machine already has all of the necessary NVIDIA Cuda drivers installed. And I can also SSH into the machine, which I've already done. So I've SSH'd into this machine. Here you can see I've already cloned these generative AI examples. I've also downloaded Llama models. I will be using, for this demo, I will be using Llama 213B chat. And even if we have a look at here, let me click on it again. Docker PS. You can see that I'm already running this example from Docker Compose. So what I have here is, as you saw on the diagram, we have a front end, we have a chain server. There's also a notebook server, which I wanted to show you, but I'm going to skip that because I'm mindful of the time that we have. But if you want, you can look at this notebook server to have a look at all of the different notebooks. All of the things related to this example are like all of the code is visible through this notebook when it comes to how do we vectorize our documents, how do we create TensorRT engine, and how do we infer. So all of these things are there's a lot of tons of code examples here, but I'm going to skip that right now. Then Milvus database and LLM server as well. So since this is already running, I'm going to show you it's this machine. So this is the how do I move this Zoom thing? Okay, I can't move it. Okay, and then if I go here, I think it's on port 89. This is the actual example running. So what you can see here is this is like, let me ask it. Hi. So we have a model 13B, Llama 2 13B model running, and I can ask it like the general questions like what is the meaning of life? Life. And then hopefully it gives me some cool answer. Purpose of relationship, personal, sounds good enough. Like, okay, cool. But if I ask it some specific question, like, for instance, what is Nebius AI? it's going to say, I don't really know what Nebius is, because it's not pre-trained, it's not trained with Nebius specific data, or fine-tuned for that matter. But there's this, like, if I use knowledge base, and you can see what I've done here, I've added a couple of documents. So basically what I've done is I've taken the Nebius AI documentation, I've taken like this first page, and I think I've taken like the second page, this page, and put it, vectorized it, and put it in the knowledge database. So now if I ask it with this checkbox enabled, what is Nebius AI, then it knows to tell me like what Nebius AI is, because in the background, a chain server has actually fetched the relevant information from the vector database and fed it into the Llama 2 model, and then it's just summarized the text. So basically, that's the idea behind RAG. You don't have to train anything. You just use the existing models. Now, if let me go back here. Now it's one thing to have like just a Docker Compose example, and you might be having similar things. So you might be having a RAG solution which is working on your a laptop, or you might be even using some proprietary models to run your RAG examples. But you might be facing the challenge: how do I take this further? So you have a Docker Compose. It does not scale. It does not offer high availability. Maybe, but it doesn't. And the thing about Docker Compose, maybe you can just scale like a virtual machine, but you want to scale these components individually. So you want to be able to scale Triton Server separately from Milvus database, and so on and so on. So, and also another thing, if the node goes down, there's no self-correcting, there's no self-healing mechanism involved. You would have to deal with load balancers and so on. Specifically for GPU workloads, you would have to solve management from all of the NVIDIA software components needed to provision GPU, like NVIDIA drivers, Cuda drivers, NVIDIA container runtime, DCGM-based monitoring, and so on and so forth. So this is what this presentation is about. How do we solve all these things? And these are the typical like product considerations that you might have for any website, not just inference or not just RAG. These are your typical utilities. These are high availability, scalability, observability, disaster recovery, CI/CD, meaning deployability, and security, of course. But I'm not going to be speaking about all of these. Specifically, I'm going to focus on these. These ones, there's specific things when it comes to scalability and observability that you need to know about when dealing with inference and dealing with the GPU hardware. So that's what I'll be focusing on. So talking about high availability, of course, choosing Kubernetes is probably the best bet because it's mature, it's reliable, it scales, it's open source, there's a huge community behind it. And of course, it has proven track records when it comes to replication, redundancy. It has cluster auto-scaling, load balancing, network policies, those kind of things. Persistent volumes, of course, another thing when it comes to storage, real important thing. But specifically for GPU, there's a specific way how we can automate GPU resource management and automate and do GPU sharing and isolation as well. I'll show that in a little bit. Observability, of course, GPU hardware. When we talk about GPU hardware, let's say it's not the most reliable thing in the world. Hardware errors with GPU will occur. You need to spot that as soon as possible. So that's why observability is a big factor here, specifically for observability on top of Kubernetes. Prometheus and Grafana is probably the way to go. There's specific metrics that you can use to monitor your GPU workloads, specifically DCGM. DCGM specific metrics can show you your GPU utilization, heat, and so on. And NVIDIA provides Grafana dashboards for these. And on top of that, also it's really important for your inference server to keep to have metrics, so you can monitor inference server as well. I'm using Triton in this example. Is not just about Triton. You might be using VLLM, you might be using something else. You might even just have your own like proprietary solution inside container, which is also perfectly fine. But you need to know that you should monitor that, and your inference server should support monitoring. Scalability and elasticity probably the most important and probably the most specific when it comes to inference. What you can do in Kubernetes when it comes to elasticity in particular, you can of course use cluster auto-scaling capabilities with GPU nodes. There's cluster auto-scaling automatically adjusts the number of nodes in cluster based on demands of your GPU workloads. And that ensures that we always have sufficient resources available for your GPU-intensive applications. Kubernetes can also utilize custom metrics from metric servers that monitor GPU usage. And these metrics are like, if you want to make informed scaling decisions, these metrics are probably the way to go. And also in Kubernetes, you can have specific node pools equipped with specific GPU resources, so you can target with your autoscaler. You can target a specific node group. So you might be having like a fine-grained nodes with just a single GPU, or you can have coarsely grained nodes with 2, 4, 8 GPUs. And depending on your use case or the workload, you can switch between those. So yes. These are like also another thing about the GPU on Kubernetes is that when it comes to NVIDIA drivers, NVIDIA has a GPU operator which fully automates your node provisioning. So I'll show that a little bit later as well. So yeah, in theory, it sounds like everything is like fine. We have this Kubernetes auto-scaling capabilities. It's just a matter of deploying your application and everything will work. But in theory, in practice, it's a little bit harder than that. Specifically, these are like the main problems when it comes to elasticity. So in the first example that I was showing you, it's just a Docker Compose. I have a single virtual machine with 2 GPU, and all of these components are just sharing the same GPU resources. Now, when we switch to Kubernetes and we switch to pods, each of these pods have specific resources assigned to them. Meaning, right-sizing your instances is really important here. So you might be having a Triton inference server with 1 GPU or 2 GPU, which are assigned to it, but then you also have like a Milvus pod, or in high availability scenarios, you have a bunch of them, and each of these pods need to have specific resources assigned to it. So probably not a good idea to give like each of your Milvus pod a full GPU. So right sizing is really important, and we'll show you how you can solve that as well. Then probably also the biggest problems with elasticity is cluster scale-up speed and as well as inference server boot-up speeds. When we in Kubernetes, when we autoscale, like in best of times, a cluster autoscale is not going to perform as fast as something like function as a service, for instance. But add on top of that each of these nodes also needs to have, like on-fly, needs to have all the drivers installed on it, and then also inference server needs to download the model, needs to boot. There's a lot of things to do when it comes to standing up a new node in the cluster. So these are the challenges that we will be facing, and these are the challenges that we want to tackle in this demo. So this is I've told you a little bit about GPU operator. Effectively, a GPU operator is developed by NVIDIA. It's a lot of daemon sets which are sitting somewhere between your pods and the actual node and OS system and the node. The daemon sets run with elevated privileges, and they're basically monitoring the system on your node. And when they notice that there's like a GPU hardware on the node, they are going to install a lot of things like Cuda drivers. They're going to install DCGM exporter, MIG manager, all sorts of things. So this is why I say like elasticity is a problem, because each of these nodes, when you stand up a new node, you need this to happen. Like you need GPU operator daemon sets to finish installing all of the CUDA drivers before a pod will be assigned to a node. And then when the pod gets assigned to a node, then only then you actually download the model and then serve a model. So it's a really long process that we want to keep under check. So yeah. Another thing I've mentioned is right-sizing your instances. Basically, with NVIDIA hardware, like what you see here is supposed to be NVIDIA H100. It can be sliced into slices. So here we see, like for NVIDIA H100, for instance, you can have 8 slices of 10 gigabit memories and 7 slices of compute slices as well. And what you can do with them is you can arrange them in a different ways. So you can make 7 slices like 1G 10 GB, which can then be assigned to a specific pod. You can slice them maybe a bit differently. You can slice them like 1 to 4. So this is also possible to have like half of your H100 assigned to a single pod. And in my example, I'm using like it's called all balanced. So in my example, I have 2 slices of 10 GB, 1 slice of 20 GB, and 1 slice of 40 GB. So I will be showing you that. And I've also mentioned that loading your model during boot up is really important. So that means storage is really important when it comes to having a read optimized storage. So in Kubernetes specifically, you have different storage options. Like out of the box, it comes with PVC support. That's persistent volume claim. The idea is that you would define a persistent volume claim, and then depending on the cloud, on the actual cloud implementation, you would get a different storage behind it. So it's like a generic way how you can define your disk. But what you need to know there is there's different flavors of PVC. There's read-write once, read-write many, and read-only many. Read-write once probably doesn't work here because we want to be able to read the same model from different pods. So you need to check whether or not you have read-write many or read-only many options available in your for your persistent volume claim. Then, other than that, you can use open source shared storage solutions. Like you can use NFS server, you can use GlusterFS. NFS is supported natively by Kubernetes. You can define NFS volumes, which then can be mounted to multiple pods, like it's going to be a shared volume. Similarly, with GlusterFS, you can define shared volume with GlusterFS. It's effectively going to give you like a distributed storage solution, which can work. And maybe also some cloud-specific things. So, for instance, Nebius has distributed managed storage solution called file storage, which can also be used here. And also, depending if your inference server supports, you can use object storage. In my case, Triton inference server does support object storage with S3 compatible object storage. So I will be using object storage in my example, since Nebius object storage is S3 compatible, so I can use it. So as I said, we have been dealing with this for some months now. So these are the optimizations we have done so far. When we, as I mentioned, the GPU operator is problematic when it comes to like boot up times. So what we have is we have a GPU operator in our marketplace repository, which means all of the containers, and there's tons of containers, are going to be downloaded via the local network, not the internet, which speeds up things a little bit. If this is not enough, we also have a pre-made image for Kubernetes nodes without the GPU operator. So it already has all of the Cuda specific drivers installed. So the provisioning will be even faster. But then, of course, some of the flexibility that you have with the GPU operator will be lost. For storage, there's always storage is always very use case specific. So we offer a range of options. As I said, we have S3 compatible object store. We have block storage based on SSD, and SSDI is our fastest option. And also additional user specific optimizations are always done on our, like we have, as I said, we have end-to-end solution. So our storage we have our own hardware, we have our own storage team. So when users come with us with specific questions, we have a direct line of communication with our storage team. So the people who are designing our storage are the people who are going to be optimizing things for our clients as well, which is a really powerful thing our clients have noticed. We are also working on marketplace marketplace for open source models. So you would be able to download models from our marketplace for ease of use, and maybe some seamless setup, seamless RAG setup. We also have a product marketplace for Kubernetes with all of these products and more, like we have Triton Server, Milvus database, even some general AI tools. We have Kubeflow in our marketplace, MLflow, VLLM, all sorts of things. I'll show you a little bit later. And of course, on top of that, we have a range of useful managed services. We have our own Kubernetes managed service. As I said, S3 compatible object storage, file storage, and SQL databases as well. We are working on more as we go along. With that said, this is like what it can look like. We've taken the original example, which was just the Docker Compose, and we've made it into something that's a little bit more production ready. And this is what it can look like when hosted on Nebius AI. So we're hosting on Kubernetes platform, and we're using a number of Nebius managed services at the back. So first, in the Kubernetes, we have the same thing. We have chain server, we have Triton with TensorRT, but these are now highly available, so I can scale these and replicate this to multiple instances. vector database, and TensorRT model can read from our object storage, and maybe even Nebius file storage, which is our managed distributed storage. For the change server itself, you might need to store sessions somewhere, or you might need to store like chat history or something like that. So what you can use is probably some SQL database in the background as well. And when it comes to deployability, we can do, like, for instance, Argo CD probably is the way to go for CI/CD pipelines here in the Kubernetes. But then also we have a Nebius console, and we also have our own Terraform provider, as well as our CLI tool, which helps a lot when deploying applications like infrastructure as a code. Regarding observability, of course, Prometheus, Grafana, you can host those in Kubernetes, and we also have, like, in our solutions library, we have examples how you can do so. Okay, and with that in mind, let's jump and see what it looks like. So let me close this one. So here in my console, as you can see, I have managed Kubernetes cluster running. I mentioned we have a marketplace. So this is the marketplace where we can choose a lot of AI ML specific products. We are also expanding on these as we go along. So for those who don't really like to use Terraform and don't know how to use Terraform or Helm, you can click your way around our console. You can probably create a similar example through our console. Like, you can create a new Kubernetes cluster. You can install a GPU operator, which is here somewhere. GPU operator. Then you can install Milvus. You can install Triton Inference Server, and so on and so on. So there's you can do it through marketplace, but probably for production, the way to go is infrastructure as a code. So we also have a solutions library, and in our solutions library we have different solutions for training scenarios or for inference scenarios as well. So for instance, this is like the example that I will be showing right now. There's a Terraform part of it, and probably the most interesting thing to show here is I will be running a Kubernetes cluster with 2 node groups. Why do I need 2 node groups? Because as I already told, is it? Okay. There's a need to have like mixed slices and full GPUs. So this node group is going to serve mixed slices, and this GPU node group is going to serve just full GPUs. The GPU operator knows how to read this label and knows how to instruct MIG manager to give me slices on this particular node. Then on top of that, there's also a Helm chart, and now in Helm chart, I can define different resources to different things. So for instance, for LLM inference server, I'm assigning a full GPU. For Milvus database, for instance, I'm assigning a slice with 2 cores and 20 GPE. And for, I don't know, change server also has some GPU accelerated things running on it. So I'm assigning a 10 GB slice on that one as well. And I have this example already up and running, of course. So if I go here, you can see that I have 2 node groups. Each of these are running just a single node. So in total, I have just 2 GPUs, basically. And when I go to workloads, we can have a look at the GPU operator. These are the, I can show you the daemon sets. These are the daemon sets that I've told you about. These are the ones which are going to be automating all the necessary things regarding NVIDIA related things like Cuda and DCGM exporter and MIG manager and so on. And so, and we also have like some Nebius specific things like this agent, for instance, which help us serve GPU monitoring. I'll show you that as well. And then if I go to default, this is where you see my example running. So now I'm running this example as pods. There's differences between what I'm actually running and what I've shown you as a production ready. So this is not really a production ready because, as you can see, it's not high availability. I'm only running this on 2 GPU at the moment. But the point is it can run in high availability setup now, which wasn't the case before. Also, I can show you if I go to a console, if I go to terminal, I can probably show you that I have assigned a mix slice to some of these specific. I'm going to use K9s. K9s is a cool tool. If you've never used it, it's really cool. So here I have my pods. For the Triton Inference Server, I'm going to shell into this Triton Inference Server. And now if I do NVIDIA SMI, see that I have assigned a single GPU to this particular pod. As you can see, MIG manager is disabled, and I have full 80 gigabytes of RAM. But if I go to, what was it, Milvus, and shell into this pod, now you can see that MIG manager is enabled, and I only get 20 gigs, right? And I think this one is a core. I'm never quite sure which one says how many core slices I have. I think it's this one. So it's 220. And maybe I'll also show you what was the other one, query router. This one should have 10 gigs, right? Yeah, 10 gigs and a single core. So that's how I've spoken about right sizing your pods. That's one way how you can do right sizing with NVIDIA mix and mix slices. And regarding observability, I haven't really installed Prometheus. I couldn't be bothered. But actually, that's not true. What I wanted to show you is how you can do observability in our console. So down here, you can see GPU monitoring thing. This is what the agent was doing. Like you saw the agent from the daemon set. This is what the agent is going to serve. So you can see here in our console, you have a full full observability of your GPU resources. And then also we have logs, which I have disabled. Sorry about that. We have Kubernetes specific logs. This is where you would see event logs from Kubernetes and more. But also like for each and every workload, there's like a whole observability what's actually running. So you have your pods running. You can, when you click on a pod, you can see like all of the events, you can see all of the logs. You can see everything from the console itself. And now another thing, like in the example, like the example said, there's a DNS and a cert manager. That's also something I haven't installed because life is too short to set up DNS for web webinars, right? So what I'll do is I'll show you the example where, sorry. So these are front-end services now exposed as node port on port 30,001. So what I'll do, I'll go to that particular node, like for instance, this one. I'm going to go to this port. And now basically what I have is exactly the same. We don't expect to see any difference in the UI, of course. It's exactly the same. And when I type in, I expect to have exactly the same behavior. But the idea is the difference between this one and the first one is that now this one is, I can scale out to this one. So this one can be scaled to millions of users, which wasn't the case with Docker Compose. So I think also in the knowledge base, I have the same documents. So we can ask him something about platform architecture. We can ask it, I don't know, KVM functions and has hypervisor. Let's ask it that. So what is and then I get that where you Nebius AI. Interesting. Maybe we should change the name to Nebulous. And then we get the response saying we're using KVM as hypervisor, which is true. So yeah, that's the demo. I'll go back to the slides. Thanks for your time. And one more thing before we end is we have a special offer. There's a QR code which can bring you to our sales representatives. We'll have a special offer for you if you want to do similar projects with us. You're welcome, of course. We will be happy to collaborate with you, not just inference, not just RAGs, but of course, if you have any training scenarios or any other AI ML related scenarios, just give us a ping. And maybe show this as well, but I think this this slideshow will be shared, I guess. So thanks for your attention, and we'll see you on the next one, I guess. But for now, that's it.